All right, our next talk is on creating the extended reality of the future with artificial intelligence and computational design. So Craig Yu is an associate professor at the Computer Science Department at George Mason, where he leads the Design Computing and Extended Reality Group. He obtained his PhD from UCLA with an outstanding recognition in research award. His research has been featured in numerous publications, and he has won Best Paper Honorable Mention Awards at 3DV and CHI conferences. He's received multiple NSF awards and regularly serves on the technical program committees of major conferences in computer graphics, human-computer interaction, and VR. Thank you, Craig.
Yeah, thank you for the introduction. So welcome to my talk. So I'm a professor of computer science at George Mason University, which is in Virginia, very close to here, 45 minutes drive. I direct a team called the Design Computing and Extended Reality Group at George Mason, DCXR for short. So to make it simple, so what we want to do is we want to envision what would be the future of work, entertainment, and everyday life be like 5 to 10 years from now, based on emerging technologies such as virtual reality, extended reality, and AI. So our interest in general falls into the areas of computer graphics, vision, and human-computer interaction. And the techniques that we like to apply to formulate our problems are optimization techniques, artificial intelligence techniques, machine learning, which I will show some examples in the coming slides. And we particularly work on the application domains of virtual reality training, augmented reality storytelling, creating intelligence user interfaces, creating new computational design tools, and so on. So there are a few major directions that our research lab works on. The first one is AI for design. So these days you may have heard of the term generative AI, right, which is pretty hot. So we have been working on this area for more than 10 years. And we use AI techniques to generate virtual environments, design, architectural design, design of 3D products, and so on. So I will show you some examples of our research work in the coming slides. And the second direction that we work on is scene understanding and AR experiences, right? So if you're just talking about popping up some virtual content in the real environment, you may not need that much of the scene understanding. But if you're talking about generating really realistic AR storytelling experiences, you need to have the computers need to have the very good understanding of the environment in terms of not only the geometry, but also the semantics, the affordances of the environment, and so on, right? So there is a very tight connection between scene understanding and the AR experiences that we can render. And we are actively working on that, especially on the areas of adaptive AR storytelling. I will talk about that work. And the next direction that we work on a lot is personalized VR training, right? So people have been using VR for training purposes for a long time, right, since the 80s or 90s. But with the AI and the machine learning techniques coming out these days, so we can also personalize the training experiences, right? So basically, you can track the user's behaviors during the training experiences, and you can analyze the behavior, and you can also have an algorithm that would adapt the training experience to help the user to improve the most, right? So using this methodology, we have created a few training experiences that incorporate such concepts. And then the fourth direction that we work on a lot is computational interaction. So basically, instead of just creating a user interface or interaction tools manually or out of a general idea, so we will formulate the interaction or the user interface as a mathematical problem with a formal formulation so that we can apply techniques such as optimization, machine learning, in order to more deeply understand the user behavior and being able to adapt the user interface and the interaction to help users to finish tasks, like navigating in virtual environments with like smart wayfinding tools, generating, exercising instructions according to the tracked behavior of the user. And also, these days we are also working a lot on VR teleoperation, approaches. Hopefully we can incorporate some AI to help facilitate the task. So lots of the work that we worked on are based on the idea of computational design. So in short, computational design refers to formulating the design problem as a mathematical problem, right? So once you formulate it as a mathematical problem, then you have a solution space, right? So you have a solution space. The design objectives help you to define this solution space, what it means by good design, what it means by bad design. So you can more quantitatively look at the design problem, right? And once you have the solution space, then lots of benefits will come, right? So you can apply, for example, an optimization techniques to help you sample some good solutions out of this space. So that's the automation part, right? That gives you the automation to sample some good stuff out of this space, right? Of course, as humans, we can, sometimes we can intuitively locate some good solutions, right? But there are many potentially good solutions in this space, and if you have a automatic technique, such as an optimization technique to sample all these gems, right, all these treasures out of the space, that will give you a lot, right? So that's the basic idea. And like in this example, you can see like you have a solution space of interior design. The red spots refer to the bad design, right? Bad design in terms of like maybe the ergonomics is not that great, maybe the aesthetics is not that great, maybe the accessibility is bad, right? So if you have some objective functions that can quantify these concepts, right, then you can define what are the not that desirable designs, right? And on the other hand, you can also find out what are the good designs, right? And you can let the optimizer, explore the solution space for you to, extract all the good stuff for you, right? So first of all, I want to talk about some early works we had on the virtual environment synthesis. So this work actually dates back to my PhD days, which was more than 10 years ago, right? This is the first project I worked on the generative design model for generating virtual environments. So I still want to talk about this work because this forms the basis of a lot of work that our group works on afterwards. So this work was published in SIGGRAPH in 2011. So the basic idea is that, well, like what I showed in the previous slide, so you can formulate the interior design problem as a optimization problem. And doing that will allow you to apply an optimizer, right? Like an optimization algorithm, like a stochastic optimizer, for example, a MCMC sampler, to explore the solution space and to sample some good solutions automatically, right? So doing that, it will give you the ability to synthesize designs automatically, right? And of course, that would give designers a leg up in terms of generating, virtual environments, right? So you can use these virtual environments for virtual reality purposes or for real-world interior design realization, right? So the general approach is you have some examples, and based on these examples are human designed, so you can learn about some basic statistics about how things are distributed. For example, the chairs are like facing the screen, right? And you may have posters which are on the wall. You may have some objects which is at the center of the room. So you can extract some basic statistics, right, from just a few examples. And then you can also incorporate some desirable human ergonomics terms such as accessibility of objects, the existence of a pathway, and so on as objective functions. And then you put everything together into the optimization framework. You apply the optimization, and that will iteratively help refine the solution and give you the desirable outcome, like I showed. So you can apply the algorithm multiple times in order to generate multiple layouts, right? So like if you have a factory, you can come up with multiple layouts which are all satisfactory with respect to the objectives that you define. So that's the general idea. But then based on this, we have lots of extension over the years. So for example, last year, we have this work published in IEEE VR, which is on perception-based scene synthesis. So basically, the idea is that you may have heard of people using virtual environment for therapy type of purpose, right? So basically, you let the user wear a headset, and then you put him or her into a different virtual environment that is more relaxing, that will trigger a certain mood on the person in order to achieve the therapy purpose. So we are motivated by such problem, such a setting. So basically, we have a machine learning model based on the neural networks to learn about the relationship between the colors of interior designs and the mood that the colors will trigger, right? So we obtain lots of interior design images with different mood tags from the Google images. We train our network to capture the relationship such that we can apply the machine learning model in the optimization pipeline, right? So the optimizer will keep asking the machine learning classifier, right? If I have this color combination, what is the mood that will be triggered, right? And you let the optimizer collaborate with the classifier in the generative process, right? And that will give you results like you can generate a cheerful dual dining room, a scary bedroom, and so on, right? And we did user study experiments to verify the results, right? So basically, we generated scenes, we let the user put on headset and then immerse into these scenes. We ask about their mood, right, triggered by the scene, and basically it matches with the, the goals that we want to achieve. Except that, moods are not like discrete categories. Sometimes one mood may overlap with another mood. For example, you may have a melancholy living room, which is also kind of scary. So we did detect some overlap between the moods, but basically it can generate mood-driven scenes automatically. So let me jump to the topic of personalized VR serious games, or people sometimes call it VR training or serious games. They're pretty similar. So one thing people have been using VR for is for training, right? So for example, for driving training, which is pretty classic example. So we have this approach, which is applying the optimization to personalize the training program. So basically, we have this setup where the user wears a headset and using the Logitech driving system, right, to control a car in a simulated city scene. And during the simulation, well, because the VR is a completely controlled environment, right? And with the capabilities of the tracking we have nowadays, such as the eye tracking, and you can also track the user's behavior, everything, right? So you can very precisely track, where the user pays attention to, right, during the training experience, whether the user look at any, jaywalkers on the wall, whether the user look at the rear view driving mirror before he changes the turn, so changes the lane. So we can detect all these things, right? So basically, we have this program, and we do a pre-evaluation on the user's behavior to see if he has any bad habits, driving habits, right? Does he always signals before he changes the lane? Does he always pay attention to things happening on the road? So based on that, we get a profile of the user, right? And we know what are the weaknesses of that user, what are the strengths of the user. And based on that, we can ask the optimizer to generate the training route for the person automatically, right? So for example, if I'm really bad at making left turns, I always have some bad habits doing that, then the training route will be adapted to help me improve that behavior. So basically, the program will guide the user to make a lot of left turns in order to reinforce the skills, right? So that's why, based on the city, we can have the optimizer driving the training process behind. And by doing that, we can more effectively train the user to improve the skills. So that's one example. Another example we have is the wheelchair training. So if you visit our lab, you will see that there is a wheelchair somewhere. And we just bought the wheelchair from eBay. So it's a typical wheelchair. But then one thing is that we modify the wheelchair a little bit. So we attach the hand controllers to the wheels, such that the user can push the wheels in order to simulate the locomotion, right? Of course, with the trackers, doing some math, we can calculate how much the user has pushed, right? And then by doing that, we can let the user navigate in the virtual environment accordingly, controlling the virtual wheelchair, right? And using this, we can generate virtual environments that help new wheelchair users, right, get trained about how to orient the wheelchair, how to accelerate, and so on, how to avoid obstacles. And using similar techniques, so we can generate different training woods in in virtual scenes, right, and then ask people to practice using this system. So another project along this line is VR biking. So you may have seen demos of people wearing a VR headset and biking on a gym bike, right? And the good thing about this is that you can, with the VR, you can get immersed into a totally different environment, right? And so that when you exercise, you're also kind of playing a game, navigating a more exciting environment, rather than just looking at the screen or the wall, right? So we have this work called exertion-aware path generation. So basically, the idea is that we synthesize a virtual world with the training path that the user will bike in the virtual environment using the setup. And the whole environment, the experience, is generated with the objective of helping the user achieve a certain exertion goal. So the exertion goal typically is you want to burn a certain amount of calories, right? So like if I really want to burn lots of calories, the algorithm will generate a more harsh training environment for me to practice, right? Like you may need to go uphill a lot, right? So that you need to push a lot in order to finish the experience, right? So the terrain, the woods, the training woods, all these things are automatically synthesized. And in order to implement the system, so again, we bought a secondhand gym bike and we modified it. So basically, we have a step motor attached to the bike. The step motor can apply a certain resistance. Can control the resistance of the bike according to the elevation of the terrain, right? So if I'm going uphill, then the step motor will control the resistance of the bike to apply more resistance, right? So that I feel like I'm going uphill, I need to push really hard in order to move forward, and vice versa for downhill, right? So in the paper, we describe the model that we use to connect the bike resistance with the virtual elevation. So we figure out the relationship and we did that mapping. And also to connect the whole thing to the exertion goal, right? So doing that allows us to generate like a virtual environment that people can practice with, and with a certain exertion goal, right? So Quincy, our postdoc, is one of the participants in the experiment, and you can ask him. He feels like he's really, the experiment the experience is pretty realistic, right? And it's much more fun than just looking at the screen to do the same thing. So recently, we also work on augmented reality-based storytelling. So we created scene-aware virtual agents. So that's a very different topic, right? So the idea is that basically you have AR stories, right? But everyone may experience the stories in different environments, right? So for example, you may have a story about a party, right? I may want to experience that story in my apartment, right? You may want to experience in your apartment. And the apartments, of course, they are different, right? So the idea behind this work is that we can adapt the same AR story to different environments, right? Depending on the context of the environment that the person is in, right? So the overall idea, this is a pipeline of the approach. So the overall approach was like this. So first of all, we need to do a 3D scanning of the environment, right? So For example, if you have a Surface Pro, so you can scan the 3D model of an environment. And we run some off-the-shelf computer vision algorithms to do the segmentation of the objects and also to deduce the identities of the objects, right? So, for example, we know there are chairs here. This is a stage. There will be a table over there, and the wall, and so on. So, on the other hand, we have the story script that describes how the story should proceed, right? So, for example, maybe the first step of the story is you have a virtual character that would choose one of the empty seats and then sit there, right? And then the next event of the story is maybe another character will grab a drink from the table and then send it to the character who has just sit down, right? So we have the story, and we have the environment, and we have an optimizer in between to link the story script with respect to the environment that the person is in, right? So that the optimizer will design like, hey, according to the script and according to what we have in this environment, where the character should go, which seat the character should take, right? And where the virtual drink should pop up, such that everything will make sense in this environment, right? And we also look at the user's position and orientation during the synthesis, such that things will be reasonable, right, with respect to the user. And this is an example in our lab. So this is our lab. We scan our lab, and this is a story about pushing for a deadline, paper deadline. So basically, the user is a blue guy, walking around, and he sees these characters, and he sees a professor working in the office, and all these things are automatically generated based on the 3D input. So we try to populate the virtual environment, virtual objects and the virtual characters reasonably, and they are having some food, in the lab table. So, this is for the lab. This is an example of showing the AR story adapted to our lab. But you can also apply this to another office that has the similar objects, right? So, hopefully, using this, we can help scale up the applicability of AR stories, right? And this is a really exciting topic we are exploring. So finally, I want to talk about one more work, which is the VR robot teleoperation. So again, this is a very different topic, but of course we are still under the umbrella of virtual reality and augmented reality. So basically, this is a project that I collaborated with my collaborators and friends from Taiwan. The major idea is that we want to be able to control a robot arm across the globe at our collaborator side to perform some tasks, right? So the first step is we want to build a system, right? And we have successfully built a system using consumer-grade VR headset, such as like Oculus Quest, right, and the controllers. So basically, the user put on a headset, and also the controller. The controller is synchronized with the robot arm, which is overseas, and we track the hand, the hand movement, and that would map to the robot arm remotely to perform the actions. And in the interface, so the user is wearing the VR headset when experiencing this, and so the user is able to control, see the hand he's controlling and the object he's controlling. So remotely there's a box, right? The sugar box. So in order to make it fast enough, right? So we apply some techniques behind the scene. So for example, we use the dope technique to estimate the pose of the object, such that what we only need to send is the pose of the object, which is just the 6DOF, right, of the object, send it over to the other side, to the GMU side, right? And because of this, we don't need to really stream the point cloud remotely that is captured remotely to our site, right? And that will help us make the connection much faster, and the experience will be real time. And we are working on this. So this is the first step. We published a IWAS paper last year on this, and we released the toolkit on the GitHub so that people can use the same thing to set up similar teleoperation system. But we are actively working on some extensions. So for example, would it be able for us to apply some kind of AI to help the user with the manipulation task? In virtual reality teleoperation, usually it's not that smooth. It's not that easy to control stuff, right? And especially if you're talking about controlling things very precisely, right? So perhaps there's some way we can incorporate the AI to try to understand the intention of the operator and semi-automate the process, right? Like for some very low-level, precise type of jobs, you can rely on the AI to perform it for you, right? And the human user, the human operator can take care of the higher level intention of the job. I want to move this stuff from here to there, and then the robot arm power with the AI will be able to finish the low-level process for you. So talking about some future directions. So one thing I feel excited about these days is, we have much stronger networks enabled by 5G or even 6G, right? And hopefully with these type of technologies, we will be able to bring AR and VR to more spaces, right? So for example, we can apply AR for outdoor experiences, like when you're hiking, perhaps based on the location you are in, you will be able to use AR to visualize wayfinding information. Same for indoor, right? Like if people are walking in a public facility or in a shopping mall, and we can generate real-time assistance to the person. And also, location-based AR, VR experiences is something we really want to explore. And also, there is lots of content that people create and put in the environment. So another direction to research is how can you manage such massive amount of data and pop up things that are really relevant to the person. And that is another topic that we want to explore. So one good source of inspiration is, because I like to play video games and I grew up in the 90s, so I always look at games when I try to get some inspiration, right? So in the 90s, we played Street Fighter like this, 1990s, Street Fighter 2, I still play it sometimes using an emulator, right? So when I play the game, I keep thinking, what would be Street Fighter like 10 years from now, right? Or like 2030s, right? So thinking about this, you can observe the gap, right? We had in 90s, between 90s and now, right? So what is missing? What is needed, right? So perhaps, if you keep working on, applying the AI for powering the virtual characters, for understanding the environment, for capturing the interaction between people, we'll be able to get there one day. Well, another game is the Mario game, right? Even earlier. So 80s, we have Mario games, 2D scroller, like a platformer game, right? What if we have the game in the 30s, right? So in 2030s. So it may be something like this. So how can we automatically populate the virtual game objects in a real park? How can you track the user motion? How can you adapt the gameplay to what is available in the real world? It's pretty fun. So I want to thank our team for working out lots of research ideas, my postdoc, my PhD students, visiting scholars, and alumni. And I also want to acknowledge the industry sponsors and the funding from NSF, Adobe, and so on our research. So if you are interested in some commercialization or technology transfer type of collaboration, so recently we also started a studio at the incubator at GMU called GBL. So we are working with some companies to try to commercialize some of the technologies we have from the lab to the marketplace. So if you are interested, please feel free to chat with me on that. And another thing is I'm doing the NSF ICOPS training. So some of you may have talked to me already. So basically, NSF wants me, I'm an academic in an academic research lab, so want me to go out there, talk to people in the industry who has experience working on like VR, AR type of development testing, to understand about the problems out there so that when we go back to the lab, we can work on useful stuff to help out. So if you have like 10 minutes to spare with me and chat with me, give me some insights, I will highly appreciate it.